welcome to today's Quantum BW colloquium. My name is Niklas Schillo. I'm part of the team Quantum Machine Learning at Fraunhofer IAO, and I will guide you through today's colloquium. Quantum BW is a state initiative for quantum activities in Baden-Württemberg that aims to bring these technologies or activities together and to create an umbrella brand to strengthen these networks and to increase the visibility of Baden-Württemberg as a quantum technology hotspot in Germany. And today I have the honor of introducing our speaker, Professor Aparajita Singha from TU Dresden. Professor Singha completed her PhD at EPFL in Switzerland in 2017, followed by postdoctoral research at IBS Center of Quantum Nanoscience in Seoul from 2018 to 2019. In 2020, she joined the Max Planck Institute for Solid-State Research in Stuttgart as a group leader, where she established an independent research group supported by a DFG Eminöter grant in 2022. And since January 2025, Professor Singha holds the chair of nanoscale quantum materials at TU Dresden and is principal investigator in the Cluster of Excellence CT-QMAT. And we are very happy to have you here today, Professor Singha. And she will today give a talk with the title NV-magnetometry, Challenges and Opportunities for Quantum Sensing Experiments. And in her talk, she will provide us with an overview over the use of solid-state spin defects, in particular nitrogen-vacancy centers in diamond as powerful quantum sensors. And she will discuss their application in probing nanoscale magnetism, including systems such as isolated magnetic molecules and low-dimensional quantum materials. And the talk will also address the role of surface effects in shallow NV centers and highlight current challenges and opportunities. And as always, questions can be posted online during the presentation. I will read them in the end, or you can ask them here in person in the end. Yes. And with that, I hand over to you, Professor Singha.
Thank you very much for this very kind introduction. Thank you for this kind invitation. It's an honor to be here today. This is a great opportunity to be able to present to you our research activities related to NV-magnetometry and how we do quantum sensing of low-dimensional systems, as you have just heard. So before I start, also because towards the end, usually there is a lack of time, I would like to acknowledge the funding. I'm really grateful for the funding from the DFG Eminöter grant and also funding from our excellence cluster CTD-QMAT in Dresden. Even more grateful for the team that is working together. So as you have heard in 25, we moved from Stuttgart to Dresden. This is a photo that we have taken shortly after the move. The group has grown since then, and there are some new faces here as well. But we are also going to hear about the work we have done when I was still in Stuttgart. So these are the former members from the group. Together, we are interested in using NV center or nitrogen vacancy center as a quantum sensor to be able to study different condensed matter systems and problems. And here I have a sketch that shows us different possible scenarios. For example, we are interested in highly sensitive magnetometry, potentially to the single molecule level. Studying electron-electron correlation in complex condensed matter environments, studying some electron dynamics or surface reaction dynamics, as well as device and transport properties at the nanoscale. So here, this is just a sketch of such a nanoscale device, for example, where one can have spin diffusion, and one would be interested in understanding as a function of current or gate voltage what kind of spin diffusion we have. An NV center, as you will see later on, which might be just a reminder to some of you, because there has been several other NV center talks also in this colloquium series before, that NV Center has this incredible sensitivity to be able to detect very small magnetic field. And so we would like to be able to harness that, as well as, let's say, some clusters of molecules, some patterned molecular network on surface where we can detect very small magnetic fields and field dynamics. But before that, let me briefly introduce my research background. So I come from scanning tunneling microscope background, both from my PhD time as well as my postdoctoral research time. And just to give you a very brief overview, what I was studying back then is magnetic fields from a single molecule or a single atom sitting on a surface in a very well-defined position. And the idea here was to see whether we can measure their static magnetic field properties, whether we can harness their dynamic magnetic properties in a way to see a prototypical quantum computing architecture. So here, this is a sketch of such a situation where we have an STM tip. And here we have the iron atom sitting on the substrate that is known to promote certain magnetic feature of this iron atom that is sitting on top. I was interested in this 4F element dysprosium atom, where the magnetic properties are coming from inner shell 4F electrons. And what I wanted to do is to study its magnetic property, both static and dynamic, right? In order to study dynamic properties of this atom, or any atom on the surface, one would have to modify the standard STM architecture with some changes. And the change here is this addition of a RF voltage here at the junction. Usually you would do an STM by bringing in metallic tip across the surface just by applying this DC bias voltage. But in order to study the dynamic property in a coherent manner, you would also have to add this additional voltage here. And if you do that and approach your tip towards the atom that you are interested in, at some point you will hit the resonance when you have sufficient magnetic field coming from the tip. By the way, this tip is magnetic. And you have a constant frequency applied through this voltage here. Then you will hit a resonance at some point when you have the energy matching condition for driving the ESR transition in this atom. And then you will see a sudden change in the tunnel current in this fashion. This is just a cartoon diagram, right? And this is how real data, for example, looks like after several rounds of acquisition, averaging, and background subtraction, and so on. So these are very small signals. This is what happens when we are measuring on a single iron atom. And this is what happens when we are measuring on an iron dysprosium, let's call it a dimer, that we created on surface using the STM tip. So what we did is we picked up a dysprosium atom from somewhere else on the surface under the tip, and then we brought it next to that iron atom that we wanted to measure on, and then we have placed it next to it within 0.91 nanometer. STM has this beautiful resolution and capability with which you can do atom manipulation, which is very well established and standard method these days. So we created this dimer, and now here you see the difference in the ESR spectra. So for a single iron atom, we see a single peak. When we have an iron dysprosium, we see the splitting of the peaks into two, right? Without going to the details, the separation between the peaks here tells us about the magnetic field experienced by the iron atom, and that is coming from the dysprosium atom in question, right? So this is dysprosium dipolar magnetic field experienced by the iron atom that I'm measuring on, right? So we measured on several such complex structures, not only dimer, different kinds of dye structures, and so on. We would always find that this ESR footprint is very, very stable. ESR footprint of a given structure is very stable. It doesn't change over the time scale of hours or even day, unless and until we shine with very high energy electrons on the dysprosium to flip the dysprosium spin from up to down. And this is what you see here as well. So these are some structures that we have created. These are just dysprosium atoms sitting on the surface. They are prepared as up, down, up configuration, for instance. And if we warm up the sample all the way up to 25 Kelvin and bring it back to base temperature to measure, we would always find them in this up, down, up configuration. So nothing changes in the dysprosium's electronic configuration and therefore on the magnetization, unless and until, which I don't show here, but we discussed that in the paper, that unless and until we shine it with very high energy electrons, more than 150 milli-electron volt, this is when the dysprosium spin will flip from up to down or down to up. Yeah. So with that, we concluded that dysprosium spin is very, very stable. The magnetization is very stable. See, T1 must be at least ours, but T2 is inaccessible because we could not drive directly ESR transition on the dysprosium atom. And we could not access its dynamical magnetic property in a coherent manner. Just a short note that recently several advances has happened in this domain of ESR-STM. There is a very nice overview here. This is a very new field of research, but it's booming right now. For example, in a recent paper, they have shown here that one can pick up a molecule at the end of a tip, and you can use this as a molecular sensor with very high resolution. Yeah. Another work is this one, SES Nano, where they have shown that it is possible to drive ESR transition on a rare earth atom sitting on a surface using this technique. In that case, however, this was done on a system where there are delocalized outer shell electrons. So we are not talking about only inner shell 4f electrons, which was the problem because of which we could not drive ESR transition on the dysprosium, for instance. So putting all of this together, I understood that even though there might be systems where very long magnetic lifetime or T1 and T quantum lifetime T1 and T2 are expected, and not only at 4 Kelvin low temperature, but even beyond, there are essentially a lack of technique with which one would be able to measure that. This is one of the reasons or motivations that I had in moving to the field of NV sensor. Yeah, so let me now briefly introduce or remind ourselves on what this is. NV center is an atomic scale defect within the bulk of diamond, right? So this is the bulk diamond crystal structure made of carbon atoms in green. Nitrogen and vacancy are the two atomic scale defects, meaning one of the carbon atoms are kicked out and filled with nitrogen, the other one is kicked out and left vacant. Together with that, if I have an electron nearby, then this trio essentially forms like a molecule, molecular bands within the bulk band gap of diamond, which is about 5.5 eV. And what we see here is just now the energy level structure of the NV center itself within the bulk band gap of diamond. And the beauty is, if we shine now with green laser, for example, 512 nanometer, it responds back with red photons. And the amount of red photons that would come out strongly depends on the spin state of the NV center. Meaning, if it is in spin 0 state, I'll have a lot more photons compared to the case when it is in plus or minus 1 state, because when it is in plus and minus 1 state, it gets temporarily trapped in this singlet state here, where the lifetime is at least 10 times larger than the lifetime in this triplet excited state. So as a result, what I essentially have is a spin-dependent, strongly spin-dependent fluorescence outcome. And because the spin information is encoded in the fluorescence outcome, one can simply look at the photon output of the NV center to know what type of magnetic environment it has around it. And one of the simplest experiments that one can do is now this. It's same in philosophy, as I showed before with the ESR-STM technique, where you are, for example, instead of sweeping magnetic field, you are sweeping here the frequency that the NV center sees, and you are measuring, instead of current in the case of ESR-STM, you are measuring here photons, right? So there's a number of photons. As soon as you hit the energy separation here, which is given by the crystal field splitting, 2.87 gigahertz in case of NV center, the system transits from ms equals 0 to plus minus 1 state in a coherent manner. And as a result, there is a sudden drop in fluorescence, right? So you see bright state and then suddenly a dark state and then back again into bright state, right? So this is how I would be able to define whether I'm in 0 state or plus or minus 1 state. And then simply one can apply magnetic field. A DC magnetic field would just split these two energy levels in proportion to the magnetic field that is applied. And then this deep is going to split into two. And this separation, frequency separation, would tell us about the magnetic field that was being applied. Now, this is the simplest experiment that one can do. Of course, with NV Center, everything is very, very well established, all different kinds of pulse schemes. I have just taken this slide to briefly mention what else one can do. Essentially, one can measure magnetic field across a wide range of frequencies, so not only static magnetic field, but all the way up to gigahertz frequencies. For instance, in megahertz frequency, what you would expect to have from nuclear spins fluctuations, you would expect megahertz frequency emitted. There you would have to essentially lock onto this AC signal with your NV center. That would be the philosophy behind this kind of pulse schemes. Whereas if you want to measure or detect gigahertz frequencies that you, for example, expect from electron spins fluctuations, you would essentially then use that gigahertz frequency to drive NV center directly. Because as I said earlier in the previous slide, NV center's own resonance is happening at 2.87 gigahertz, subject to magnetic field. So you can just use this gigahertz frequency to drive the NV center into resonance, which is oftentimes called relaxometry measurement. Plus another small table that explains and compares different types of state-of-the-art magnetometry technique based on scanning probe method. For example, MFM, squid-on tip, squid subtometer and squid-on tip, and scanning NV-magnetometer. This is from this review paper that compares these different techniques across all different types of parameters. In my view, where scanning NV-magnetometry stands out would be here, where the sensor size is essentially atomic scale. So the sensor size is basically atomic scale defect, so it can be less than a nanometer, and the operational temperature. So it's not just, it is operational at low temperature, but potentially it is a room temperature qubit and a sensor, but potentially it can also be used for sensing beyond room temperature. So this is a massive difference as compared to other contemporary techniques when it comes to quantum sensing. With that, this is what I have now in the group in TU Dresden. These are the two setups that we work with. On the left-hand side, we have a confocal setup that we use. I will show you in a short moment, where we use arrays of sensors to probe our molecules or material of interest. And on the right-hand side, we have a scanning probe and the magnetometry setup. This is a bit of a zoom in, where you see that this is the measurement head, essentially. And another zoom in shows you that this is the tip with the objective sitting at the cold plate, it's a 4 Kelvin thermalized plate, and this is where the sample will come from top-down approach or configuration. Recently, we have shown in this work that one of the key challenges in NV community so far has been how to apply the microwave frequency to drive the NV center into resonance. And oftentimes, usually, this is what people do, they put the microwave strip line, for example, on the sample. So then wherever you are close to this wire or strip line, only in that region, your NV center will be getting into resonance, and you are limited to that area of your sample for probing, for instance. We thought of another way of doing this, which would be carrying the microwave onto the tip itself, onto the tip holder itself. Yeah. So for that, we had to design our tip holder such that we can deliver the microwave using this antenna. This antenna containing tips are already possible to purchase from QSaper, and then we modified our tip holder such that we are able to basically bring in the high frequency with the tip, so that we are not limited to certain area of the sample. We can see that our own version with the gold wire carrying the microwave onto the tip versus the antenna configuration, we gain much more in the antenna configuration. We have much more power to the tip. We have much better Rabi response. We have much better ODMR or ESR contrast from the NV center itself. On the right-hand side, as I mentioned very briefly earlier, that we use this setup as a confocal setup where we have arrays of NV center. So basically, this is a chip, diamond chip, that we either get it from our collaboration with Professor Rachtor's group here in Stuttgart, or we buy it from QSaver, where we see that there are such arrays of pillars. In each of these pillars, we can have a single NV center, or we can actually verify that we are looking at a single NV center situation and not multiple by doing autocorrelation measurement that I will show you later on. And essentially, you can then put your material on top to look at one NV center at a time. And this is just a brief look into the optics, which is basically well hidden under the tall cryostat tower that you have just seen in the previous pictures. So with that, let me now show you one of the things that we did related to sensing molecules on arrays of NV nanopillars. And this was a study where we were interested in looking into NHC60 molecules. So in powder or in bulk, they are known to be very good qubits of very well-known properties. We wanted to understand whether it is possible to detect them at a single molecule level, and what would be the modification in their properties that we would see in this case. So again, these are the arrays of NV nanopillars. We would choose one of such nanopillar. We would deposit, drop cast the molecules of interest. And in this case, we have, for example, NHC60 molecule drawn in this fashion, where we have the nitrogen atom drawn in yellow. But we have to also prepare the sample in such a way that statistically, we have only one molecule out of many that are empty. So only one molecule that gives us magnetic signal, and the rest of them are not. And we do that by doing this dilution, where we have most of the or rest of the fullerene molecules empty without any nitrogen atom in it. Then if we shine green laser, collect the red photons, apply gigahertz frequency for the NV center, for the molecule of interest, for bringing the molecule into resonance within its own Bloch sphere in coherent manner, and focus on one pillar at a time, then we will be able to apply different pulse schemes to measure ESR signal from the molecule itself. Yeah? So here on the y-axis, we are plotting the photon output from the NV center as a function of detuning frequency, or as a function of frequency, let's say, that we apply on the molecule itself. And what we see here are the resonance, and this is the single spin EPR spectra from the NHC60 molecule. The reason behind this triple deep structure is coming from the molecular electronic structure of this molecule itself. It's a spin 3½ molecule, so you have -3½ to +3½ all different levels. Also, this is hyperfine coupled. So the hyperfine spin is 1, so you have 0 and ±1 states possible, which is why if one does the calculation with the Hamiltonian, we would end up with these 3 deep structures, which is also consistent with the bulk EPR structure that we see in this molecule, which is shown here in the dotted line. The reason behind slight shift from these dotted lines, or from the bulk EPR fingerprint, and the reason behind having stronger intensity at the central peak versus the others, this can all be explained to a good extent by the fact that when the molecule lands on the surface, it does not have its spherical symmetry absolutely preserved anymore. It is deformed, right? So all those parameters related to the molecule are also changing. So those can explain slight differences, but I wanted to show you this as a proof of principle that one can indeed look at single molecules, single NV center interaction to get a single EPR feature using a non-invasive method, or least invasive method, because all we are doing is counting photons while interrogating the molecule electrically. This is not a given thing in other type of measurement. Again, taking the aspect of STM, what I showed very briefly in the beginning, you are interrogating electrically, and you are getting the response out as current. So you're also getting an electrical response out. In this case, the readout and excitation mechanism are isolated. You are detecting photons, so you're detecting optically and interrogating the system electrically or electronically, which is what making it least invasive. And then you can also park yourself to one of these transitions, for example, in the central transition, and you can also apply this type of Rabi sequences. This is on the NV center, this is on the molecule itself, because from the previous experiment, EPR spectra, we know now what type of pulse we need to apply here in order to get Rabi measurement. So this is Rabi oscillations on the molecule, again detected by the photon modulation on the NV center. Now we are taking this forward with different other types of molecules where potentially we can even form networks. And this is one such example where we are looking at this TTM molecule. Here, this is the basic building block. The idea here is we can have such chain type of molecule where we have several numbers of radicals at different distances. The idea is whether we can detect again this presence of the radical using single NV to single radical interaction and dipolar coupling. Here, one of the interesting thing is these radical species are very stable at room temperature. So one can potentially do any of these experiments also at room temperature, but also, of course, at low temperature, which will be the next thing for us to explore. But for now, this is the idea that we will again dilute the system in such a way that we have only few radicals within the detection volume and rest of them are not giving us any magnetic signal. And here I have on the left-hand side a confocal scan. So this is how the array of NV centers would look like, where we have only few bright dots. And we will go, for example, to one of the brightest ones, choosing, let's say, this one. And then we will try to see whether this has any molecule on it or not. One of the quickest, well, not really quickest, but one of the easiest experiment that one can do is to measure the T1 time of the NV center with and without the molecule. For example, if the radical is present on top of the pillar where we are measuring on the NV center, the radical will have some spin noise. And if the spin noise creates a noise at the frequency where NV center is resonating, we should be able to catch this using T1 relaxometry, right? So this is, for example, it's a very preliminary data. We still have to reproduce it after we have moved to Dresden. We have just initiated these experiments again since a couple of weeks ago. But what we see here in this preliminary data is we see a reduction in the T1 time from 11 millisecond to 2.7 millisecond upon adsorption of the radical species on the pillar. And we interpret this as interaction between the radical and the NV center, but of course we will have to verify this further by looking at different concentrations, by looking at different nanopillars so that we get better statistics, and also not only T1 relaxometry, but probably we should be able to capture this fingerprint by doing other types of measurements as well. With that, I would now like to move on to the next part, which is related to diamond surface chemistry, and this is part of the challenge that I had in the title of my talk. So when I moved from STM to the NV Center community, I realized this is one of the biggest, if you want to call it, bottlenecks in the community, that diamond surfaces are very ill-defined, and it can be very different from my preparation to your preparation. So that would also have a huge effect on the results that we see, right? And again, coming from the STM background, this was a very surprising thing for me because not only STM, from surface science community, this is a very surprising thing, because if you don't have a very well-defined, well-reproduced surface, then you can have all kinds of surface effects that you will see in your results as irreproducibility. So what happens is when you have shallow NV centers, shallow meaning within 10 nanometer from the diamond surface, because of the modifications that can happen at the surface, that can be due to implantation of the NV center or the nitrogen atom into the diamond, that can be due to any other effect, the NV center oftentimes loses the electron that I introduced at the very beginning, that it's nitrogen vacancy and an electron. And if the electron escapes the NV center, then you essentially have a charge state instability, which is directly linked to the spin properties of the NV center. So you are dealing with a very unstable NV sensor if you want to come closer to your sample of interest, right? And this happens already within 10 nanometer from the surface. So since we have in our group ultra-high vacuum capacity, which means we can reproducibly prepare our surfaces, we wanted to take up this challenge to see whether controlled surface modification of the diamond would bring about any solution or not. So we tried absorbing different kinds of molecules on the diamond to see what happens to the shallow NV center. We have always some markers on the diamond chip so that we know that we are measuring the same NV center before and after the surface modification. And what we saw is, let's say CO or nitrogen or argon or other kinds of molecules would have no effect, no reproducible effect. But if we dosed water on the diamond surface, we would always see a positive effect. Here I have autocorrelation measurement, which basically says whether I have a single photon source or not. So we are measuring this NV center by using two avalanche photodiodes. And if it is a single NV center producing the photon in the way that we expect it to, then we would see the single photon output in one of the NV center and not on both of them at the same time. This is the key aspect. So that means I should have this value close to actually 0 ideally, but less than 0.5 in all experimental practical aspect, if I have a good NV center, right? And our optics is set in such a way that if I have a charge state instability and the NV center has lost the electron, then it is NV0, I would not see this signal anymore. And that is a good indication for me that I have lost my NV center as a good sensor, right? Now, the green one is actually the case where we have dosed water, whereas the previous situation is the cyan one where we have no water dosed on the diamond surface. So as soon as we bring the diamond into our UHV chamber in low temperature condition, we have the autocorrelation measurement completely gone. And we revive it only after dosing water on it. I have another overview on not only autocorrelation measurement, we have seen this on spectrum, fluorescence spectrum, on ODMR spectrum. So for example, in the center, this is the autocorrelation. In ambient condition, we see autocorrelation measurement on the same NV center is intact. In low temperature UHV condition, this is killed. When we when we bring it outside again in a room temperature stage, it is revived again. And the same scenario we see on the fluorescence measurement. So this gray one is a fingerprint of the correct charge state of the NV center, which is NV minus. And the red one is the NV0 charge state, which is what happens in the low temperature UHV. And the same story holds also when we look at ODMR response. So this is normalized fluorescence as a function of frequency. And this is the case when we have dosed water in low temperature stage. So this is what you see, that in the low temperature stage, we had, without water dosing, this red curve. And after water dosing, it has shifted to the higher wavelength, which is a characteristic of the correct charge state, the negative charge state. And we revive it on the autocorrelation as well as on the ODMR. Of course, the ODMR contrast is not as good as we had in ambient condition, right? So we don't have a very high contrast. We have just a few % of ODMR contrast recovered. But this already proves or sets us as a proof of principle that surface modification, if it can be done in a controlled way, would bring about the correct direction. At least it would help us solve one of the several reasons why NV center is so unstable in a shallow configuration. This motivated us, as I said, water is a physisopt material on the diamond surface. So we were looking for now a more stable, chemically reproducible solution. And this is what we did as a follow-up to this project, where we did atomic layer deposition coating of titanium dioxide on this nanopillar array of diamond, where we have several NV center in an array. And now I show you that this is the before and after the titanium dioxide dosing on one representative NV center. So the green is clean and the purple is coated. You already see that we see a very strong increase, an improvement in the ODMR contrast. And also you see a very big improvement in the Rabi behavior of the NV center, which also relates to the fact that we will have better sensitivity. And in fact, just to give you some figure of merits, we have been able to improve B field sensitivity by almost 25%, almost 80% increase in the NV minus population, which we can see from spectrum, fluorescence spectrum that I don't show here. But we also see 45% increase in ODMR contrast. So all numbers are in the good direction. So we have been able to improve significantly the figure of merits for several NV centers. This set comes from about 17 or 20 NV centers that we have been able to track before and after the titanium dioxide coating. I want to highlight that these measurements are done at room temperature, but at very low pressure, less than 10 to the power minus 9 millibar. If we don't do any coating, there is no NV center, or almost probably 1 out of 50 that we would look at work, and probably that would work. So only with the coating, this brings us to a very good statistics that most of them would work. Now, why titanium dioxide? Why does it work? What are the structures, or what is the structure of the titanium dioxide on the diamond surface? All of these are open questions to us. We are trying to establish some theory collaboration, and also, as I said, this works only for, right now, this has only been established for nanopillar membranes of diamond, where we have NV center on each of these pillars. But of course, the main motivation is to be able to do that also on the NV containing scanning probe method, or NV tips. This is a work that we are now pursuing in TU Dresden. Whether this will work or not, and if it works, that's good. If it doesn't work, we also have to understand why it didn't work, or what other types of coating would also be beneficial. These are all open questions to us. And this is what we are trying to explore further in this domain. With that, I am at the very last section, where I would like to show you now some aspects of using NV center for looking at nanoscale devices or nanoscale materials. So to speak, some opportunities again. In this regard, NV center has been used for studying surface magnetism on various different complex condensed matter systems, and I obviously cannot cover most of them in 1 or 2 or 3 slides. It's just a very vast community. I have picked out just some examples. For example, vortex stray field imaging, imaging of skyrmion, all kinds of novel 2D materials in different complex geometries, bilayer, trilayer, with different twist angles. Very recently, this is also what has been done in 2 different geometries, where you have 2 NV centers looking at, let's say, looking at a shared and a non-shared noise, so correlated and uncorrelated noise. And this is when the NV centers are part of the diamond crystal itself, diamond substrate itself, and imagine that you would have to put your material on top. The other geometry is on the tip, where you have the sample here, for instance, and you have 2 different NV centers on the same tip, more or less at the same location, but they differ in color, in frequency, right? So you can interrogate each of them at different frequencies. And with that, you can really learn a lot about the length and time scale of correlated phenomena occurring on the surface, which is, I would say, a major breakthrough or game changer, something that one cannot easily do in other kind of scanning probe system. So my group is also interested in this direction, and I would now show you a few results related to, let's say, surface magnetism. Here we used our home-built scanning probe setup to look at a 3D magnetic field structure of a 3D sandwich system. So each layer in this case is cobalt platinum is ferromagnetically coupled, but in between the layers there is antiferromagnetic coupling because of the spacing of cobalt ruthenium. And we first wanted to see whether we can see any magnetic field feature using our NV center. This is raw data with scanning NV measurement, where we were just scanning across the sample to look at what sort of magnetic field we are looking at. This is not really a direct measurement of magnetic field, but we were looking at photon output, right? So imagine where we have strong decay in the photon output. This can be interpreted as very strong magnetic field, which causes spin mixing, for example, in the NV center, and as a result, you don't have very good photon output anymore, right? So here, then this can be interpreted as ferromagnetic domain wall, and these are the antiferromagnetic domains. Yeah. We also did T1 measurements on the NV center by parking our tip either here or on the domain wall, and we see a strong difference. So for example, this tip had a T1 time of about a couple of milliseconds when it was retracted away from the sample, whereas in contact or close to the sample, we have strong variations depending upon where we are on the sample. And one would expect that also because your spin noise from two of these different regions would be very different and affecting the NV center differently, right? But just to highlight that also on the AF domain, you do pick up some signature of this magnetic field fluctuation, because locally there are still some spins that are fluctuating, and this will affect locally the NV center spin, even though overall this is a compensated antiferromagnet. Another highlight from the same sample is we were able to image then by doing ISO-B magnetometry, the zero field line. So this is the one shown in white color here. So essentially you are imaging at two different magnetic field and you are doing a subtraction. As a result, you can fine tune exactly the position of the domain wall and so on. Somewhat related to this work is when we measure with NV center, we always measure magnetic field, but we have no understanding of the magnetization, right? Because magnetization is not something that we directly measure. And this conversion from magnetic field to magnetization is very non-trivial because you can have several different magnetization giving you the same magnetic field. Yeah. And this is also one of the things in the community where there are several different approaches taken to do this conversion from magnetic field to magnetization, because magnetization is the telling feature of your sample and you want to know that. One of the approach would be Fourier transform based approach, where there are several prior knowledge of this sample that you can use to constrain your model, and then you would be able to reconstruct the magnetization. The other approach is machine learning based approach, which has been taken by a couple of other groups since almost 2022. So rather recent. We are also developing in this direction, not only to do this conversion very well, but also to define uncertainty. This is something that is missing also in the community somehow, that when you reconstruct magnetization from magnetic field maps, what you typically see in the literature is this is the magnetization map, but you don't know what other several different magnetization maps would also satisfy the same solution, and what are the differences, or how unique the solution that we have found out, right? So we have developed an approach with which we can define this uncertainty, and this is a snapshot from a recent paper that we have submitted where we say, for example, stray field cannot be the telling feature of very complex spin configurations such as topology or topological charge. Yeah. So we showed here that you could start from very different magnetic field, very different magnetization, corresponding to very different topological charges. But with such a construct of loss function, you can always end up in a situation where your stray fields are matched. So your two stray fields will be the same, with a very distinct set difference between the topological charge and very different magnetization profile. Meaning, you can have the very same magnetic field giving you a constant difference in the topological charge. So just by looking at stray magnetic field, one wouldn't know about the topology of the system. And this was just a formal way to show it in this paper. Very last topic would be looking at devices, like I promised earlier. And this is just an example of what people have done. It's possible to use NV-magnetometry to look at nanoscale devices, to look at current distribution, for example. This was a case of a graphene device in the previous slide. We did this in a spin Hall nano oscillator. These are nanoscale constrictions in the material. For example, in our case, we had platinum and nickel iron, and we made this nanoscale constriction in which we would be able to, let's say, localize gigahertz oscillation in terms of this concerted motion of the electrons because of spin Hall effect in the system. If we now put the current in another direction, we would not see this. So this is a direction, there is a directional effect in this. And the idea was whether we can measure this concerted motion of electron using a scanning NV that is scanning across this constriction area. And the answer is yes. So this is how our constriction looks like, again, in the photon counts from the NV center, scanning NV center. And we saw that not only that we can locate the regions from which we have the gigahertz oscillation created, we can also tune by applying different amounts of current. We can also tune where this is mostly located. So in the lower current regime, for example, for this particular device, it was located around the lower part of the constriction, and at the higher current regime, it is located around the upper part of the constriction, and so on. And the philosophy goes like this, where we have, let's say, this is the case of an NV center getting into resonance without any auto oscillation. So we have switched off our nanoscale device, gigahertz oscillator, and this is just the standard ODMR like I have shown you before. The fact that it appears at 3.57 gigahertz is because we have a magnetic field applied, so the resonance is pushed forward. And then on the right-hand side, now we don't do ODMR in the standard way. We switch on our SHNO, spin-hole nano oscillator device, which emits the gigahertz frequency. And it emits the gigahertz frequency at a certain DC current, right? And this is what you see here. So if we now collect the photon output from the NV center, we are suddenly going to see a dip at a given current around 12 milliamp, because this is where we did also electrical characterization of the device, and we know this is where it emits the gigahertz frequency, where the NV center will get into resonance. And of course, as I said earlier, if we reverse the direction of the current, we won't see this transition anymore. So with that, I have arrived at the end of the talk. I have shown you three directions that we are taking up in our group. One is related to sensing molecular spins and networks. One is related to diamond surface chemistry to stabilize shallowly implanted NV center, both optically and from its spin properties, so that we can import this knowledge into NV tip. And the last is about looking at nanoscale devices. With that, let me thank all the collaborators, team members that I have been blessed to work with. Looking forward to much more collaborations and fruitful work in the future. And thank you all also for listening.
Yes, thank you very much, Professor Singha, for the nice presentation. Other questions from the audience here? Okay. If not at the moment, I have a question. So, can you comment again on the advantage of using NV-magnetometry at room temperature, apart from the fact that you don't need a cryostat for that?
That's a very good question. So using it at room temperature, this is one of the main advantage, of course, that you don't need cryostat, don't need to pay for the helium if you are paying for it. The other advantage is there are several systems that do not require low temperature measurement. So there are several stable molecular systems, some of which are also lanthanide containing. Well, in that case, this would not be at room temperature, but this would be at, let's say, close to liquid nitrogen temperature. But even there are not a lot of other possibilities where you can use a very sensitive quantum sensor to look at them. So if it is about beyond 4 Kelvin temperature, there are certainly several such use cases where one can use the NV center.
Thank you.
There are no questions in the chat. There's one question in the chat. It just popped up.
So there's one question. So can you say that the tip probe magnetometry is modern, non-invasive NV AFM?
If we can call it modern, non-invasive NV-AFM, yes, that's exactly what it is. It is based on AFM technology. I didn't mention that, but yes, it is actually operating as an AFM. The main difference is instead of measuring the force as the only thing, you are measuring the force in order to stabilize the junction, etc. But then you are measuring the photon output from the NV center to know about the magnetic properties that you're interested in. I think we can also call it non-invasive or least invasive because of what I also briefly mentioned during the talk, that oftentimes you can interrogate the system by applying current, voltage pulses, or high frequencies to the sample, whereas you are collecting the response of what you are wanting to sense can be sensed by looking at the photon counts. So these two channels are separated, which is what makes it least invasive, because your readout and excitation channel are not the same.
Thanks. I also have one more question. So actually fabricating the samples, so to me it seems it's more complicated compared to other magnetometry methods. Is this the case?
Really, the samples or NV center tips or
more the samples actually. NV centers probably also the big bottleneck.
It is, yes. So I mean, there are two sides to it. So NV center, preparing the NV center in the shallow configuration in a reproducible manner is a challenge, like I said. But yes, from the sample side, depending on the sample, it can be difficult. For example, very soon we will start a project on a system called platinum bismuth 2, where you can get this as a very nice bulk material, but then we would have to exfoliate it and have it placed on the diamond nanopillar membrane, which can be technically tricky, and so on. So these challenges are there indeed. So depending upon the sample, it can be tricky to get there on the measurement head.
Thank you.
I saw another question there.
Thanks for the talk, first of all. I have a question if you maybe could repeat how to use advanced machine learning techniques in this setting.
Yes. So maybe first I go back there. Yeah. So what is being done now in the literature are, for example, you start with a guess magnetization map, and then you try. So from magnetization to magnetic field is easy conversion. It's a trivial one way, right? One-to-one mapping. So from that guess magnetization, you try to create your magnetic field map, and then you compare it with the experimental measurement. So it's basically it's an advanced fitting algorithm. That's how it is being done, and one uses machine learning in order to basically expand the space in which you can use lots of parameters to have this guess magnetization, and so that you are not trapped into one local minima, for instance. In our case, we are also using basically that. What we are doing, for example, in this defining uncertainty in the reconstruction algorithms. So what we did in the work that is currently in preparation, we used Monte Carlo dropout approach. This was one of my postdocs. His idea was to, let's say, abruptly, so by Monte Carlo approach, dropping out some of the parameters, some of the channels in this whole algorithm, and see what kind of magnetization map I would produce, and subsequently what kind of magnetic field map I would produce, and random dropping out of parameters has what kind of effect on the end result, should give us some uncertainty estimates. Because if it relies on certain parameter in a certain way, either it is directly related to the physics behind the sample, or it's because we are trapped in a local minima. So this kind of definition of uncertainty map is not there right now. So we are using that approach in that way.
Okay, are there more questions? If not, then let's thank Professor Singha again.
Thank you very much.
Our next session will take place on October 1st, where Professor Alexander Ling from the Center of Quantum Technologies in Singapore will be presenting his work on space and the quantum internet. So thank you for your attention and have a nice day.